the overall introduction of the LBE, so we're going to keep that in mind. Especially, I think the key takeaway is that we have several variables that we deem sensitive and we want to synthesize them. Okay, and then all of the variables, I mean, many of the variables come from different types, so we'll have to figure out a way to synthesize them correctly. So the first thing I want to talk about is, what if you have more than one variable you want to synthesize? The paper or the application did in the was done in the CLBD is very typical in a sense that when people are dealing with this situation, they have more than one variables to synthesize, they typically go with the sequential synthesis procedure. So let's first look at what they did in the LBD, and then let's talk about like why you can do it and how you can do it. So this is the original table that we saw earlier. And if you read the paper, you will notice that they were doing in a sequential way. So first of all of the X's are not like either not released or synthesized, but they're used as predictors because they can be really helpful. So that's what they think. And most of them are categorical, FYI. So so starting from, so I guess that's why they're labeling them in this way, because they're doing it sequentially, Y1 through Y5. So Y1 is first year, is a categorical variable. So they first of all synthesize categorical first year given X1 and X2. Okay, so X1, X2, they're always some kind of predictors. We're going to go into the detail later about how these models are being developed. But right now, just get a sense that X1, X2 are always being conditioned, meaning that they're given, or you can think of they're the predictors for whatever models they're doing. So when you have that, then you can generate or synthesize first year from this conditional distribution. We don't know what it is now, but let's use S generically. And then once you have done with first year, you can do last year. So sequentially, they're doing Y2. And you can see that their construction is you are doing that given not only X1 and X2, but also Y1. Okay, so that's what they mean by sequentially. Like I do one first, I finish Y1, then I move to Y2. And for Y2, I use Y1 and also X1, X2. Okay? And soonish you will see their setup here is with multi-unit, which is Y3. That is from a conditional distribution or conditional model here, given Y1, Y2, and X1, X2. And then for the last two, Y4 and Y5, because they have this time component here. So for example, for employment, they're not only using X1, X2, and Y1 through Y3, because these are already done previously. They're also using the previous year's employment as one of the predictors. Okay, so that's why you can see this kind of notation that for the current year T, I'm building a model given the previous year's employment and then everything else that I have done so far. Okay. And lastly, for payroll, I guess it's natural that you not only think about the current employment, but also the previous year's payroll as one of the predictors. And then everything else you have done. So this is what they mean by sequential synthesis. And I should just mention that in practice, this is very common. And as you can see, it is straightforward in some sense that if I know, like say, how to model categorical variable, how to model, I mean, there's no binary here, but what if I have a binary? If I know a way to model and synthesize each variable, like univariately from one variable at a time, I can always do this kind of sequential. I mean, you might be wondering, okay, what will be the right order of the sequential and all that? So, well, that's all legitimate questions. We should keep those in mind. For the seeing LBD, that's what they did. Okay, and I think it sort of makes sense. I mean, first year, well, you should generate the last year given the first year, right? I mean, if you don't even know first year, well, yeah. Anyway, so I think to some extent it definitely makes sense. But you might argue, okay, why don't I do multi-unit first or whatever? I don't know. To be honest, I have no idea. Maybe you want to do that first. There must be a reason. I mean, when they're developing these methods, that they did this in this particular order. And to me, I think it makes sense that you do employment first and then do payroll. Okay, and then also within employment, you want to use the previous year's data. That makes sense. And for payroll, you probably want to use the previous data as well. Right? So that's a general procedure, and we should all just keep this in mind. Because I'm fairly confident that for your project, you're going to do some kind of not just for one synthetic variable. I mean, not just for one synthetic variable. You might want to do multiple, and then this sequential procedure will be something that you can use. But you might be wondering, okay, why can we do that? So this actually dates back to a different method, or like a related method. They call it FCS. Stands for fully conditional specification. Don't worry about the name. But synthetic data, the method itself actually had some history in the past, that when you have missing data problems, like when you get a survey, you have some values or not, like reported or not reported, or for whatever reason was not available to you, then there are a lot of methodology being done in the past, and even now as well, people are doing the research for, is how to do imputation, like how can you like fill in those missing data, okay? And the method, one approach does, is what they call the fully conditional specification. And it's pretty much very similar to what we're doing now, thinking about the full synthesis. You can think of, so missing data, for example, you have like a data frame. And I have multiple new rows. Each row is an observation. I have multiple columns. And let's just say some of them, I'm just going to use a question mark to represent any values that is not available. Okay. Well, this is an example. So Bayesian methods, typically for those problems, is to try and build model for the variables and then trying to generate value from the model to impute. Okay, so it's very similar in some sense to what we're thinking now about synthetic data. The difference is for synthetic data, we assume that there's no missing value, right? We just develop a model on the original fully observed data, and then we act as if there's some missing. Like you can think of all of the sensitive ones as missing that we're trying to compute. Okay, so that's why when synthetic data was first proposed, or like in the beginning years, people were using the word like, we're doing multiple imputation for disclosure limitation, something like that, okay? But that was beginning. Nowadays, I think people more and more accept the terminology of synthetic data, but the general method is not that different. And the fully conditional specification, you can think of it as I'm focusing one column at a time. Say if I'm doing it in this order from left to right, I first of all develop a model and then fill in. Let's just say I got this right. And then I move to the second column, which is the second variable, sequentially. And then when I develop a model, I will also use the one that I just did. Okay, so that's what they mean by fully conditional specification. I'm doing one at a time, and I'm trying to condition on what I have done so far. So in the synthesis perspective, like the synthesis world, what we're doing is if you have several variables to be synthesized, then you can sequentially synthesize one variable at a time, given what has been synthesized already. So the methodology is very similar. And I think overall the idea is intuitive. Like, yeah, I'm tackling one at a time, and whatever I have done already, I try to use what I've done. So you're doing it sequentially, but every time making sure that you factor into what you have done already. So you might be wondering why sequential synthesis works, okay? Like mathematically or statistically, whether it works or not. So I should mention, if you have a table, sorry, not a table, like a data frame, we have multiple rows, multiple columns. Each column is for a particular variable. If you are able to, so just think about synthesis. I want to develop a model to best estimate whatever that I'm trying to do. So if I have like 4 variables here, if I can develop a joint distribution, joint density for all of them, if that is a good model, I might just be done with it. In a sense that well, if I can, and in fact, many people are trying to develop a joint density for all variables if they can, because in theory, that will be able to capture a lot of things if you can have a joint distribution. Yeah, so we haven't, yeah, so that's the thing. I think in 347, we haven't talked too much about joint density, or we talk about like joint distribution, like joint prior and all that, like joint posterior. For here, think about joint density as what if I can specify, so for the CE data, we have income, right? Income, rural, urban, expenditure, and race. Okay. Yeah. So when you have a survey like that, in a sense that you have two continuous, one categorical, one binary, it's already pretty clear that it's really challenging to specify a joint model. Not surprising, right? But what I want to say is when people are trying to do this FCS, in the sense that they're doing sequential modeling, what they're trying to do is they're trying to approximate the joint using a sequence of conditional. Okay, because at the end of the day, we want a good joint distribution, or if we can estimate the joint distribution. But sometimes, I mean, many times, it's just so challenging to do a joint distribution to start with. Like I said, if you have all kinds of variables, and each one needs a different way to be taken care of, wow, how hard it is to do a joint distribution, right? So if that is the case, then the sequential synthesis, or FCS, the full conditional specification, that will be less challenging to do because you can deal with one variable at a time. But at the end of the day, your goal is to get a good approximation to the joint. Okay. So let me show you what I mean by that. What do we mean by a good approximation? So for illustration purpose, I'm ignoring the t, the time t, for the y4 and y5 for the models that we did. So I'm just doing it y5 through y1. So look at what's on the left. The left is the joint distribution, joint density of y1 through y5, given x1 and x2. x1 and x2, they're always predicted. We don't worry about them. They're created, or they're not released, but they're used. And on the right-hand side, well, now I think of it, I should probably do the reverse order, because you do y1 first, and then y2, and y3, and y4. You know what I mean? Like on the right-hand side, like the order. But at the end of the day, you know that when you're multiplying all of the conditional in this way, you will get to the joint. Okay. So let me just do a quick demo here, and then you will see what the rest goes. So I have y1, so this goes back to, I guess, the probability class. If I have these two conditional multiplied together, what do I get?
F y1, y2 given x minus 2.
Yep. Right? Yeah. So, well, yeah, I hope everybody can refresh your memory and get to this point. So x1 and x2, they're always being conditional, so you can just ignore them. They're always there. And if you just focus on, so if I focus on fy1 and fy2 given y1, I know that the product of the marginal and the conditional is the joint. Right? So that's from probability, of course, but I think in Bayesian we talked about that as well. Not as much as what we're trying to do now, but the product of the marginal and the conditional will get you the joint. Okay, so the last two gives you the joint of y1, y2, right? And then you see that immediately on this line, y1, y2 are being conditioned. So the last three are going to give you the joint of y1, y2, y3. The last four are going to give you y1, y3, y1, y2, y3, y4. And the last one, once you include everything, going to give you the joint of y1 to y5. So I'm doing it in a simple way that I didn't consider all of the, remember for y4 and y5, that employment and payroll, they have those T, right? They have multiple observations. So for simplicity, I'm writing over here, but I'm sure even if you include those, I mean, the math's going to work out in a sense that you will get the joint as you want, right? And the product, again, we know that this is, I mean, probabilistically, we know this is true. Like the joint will be the product of, the sequence of product of the conditional, sequential conditional. But at the end of the day, the right-hand side could be a good approximation to the left-hand side. The left-hand side is the joint. We don't know what the joint is, so that's the key here. We're trying to approximate the joint. The joint will be really challenging to do if you have multiple variable types or all kind of constraints that you can think of. Then instead of working with the joint, you can work on the univariate conditional one by one, and then make sure that whatever you have done, that should go into the conditional for the next stage. And that's the key. I mean, otherwise this wouldn't work, okay, mathematically. So this is what we are with right now. I guess really quick, this is similar but different from give sampler, right? So give sampler, well, what do we do for give sampler if we try to write a mathematical form, or roughly, like what's the distinction between this and give sampler? Let me just pause here. We're not doing the same thing, obviously, but I do want to mention, compare them over here. There, we're doing it sequentially too, one parameter at a time, right? But what's different there from here? Continue. What do you think the distinction between what we're doing here and give sampler?
In good sampler, we use we're kind of looking for convergence, so we use data we generated in previous iterations to inform our current approximation. Whereas here, we don't want to do that because we want to just generate like one value for in this like instance of y1, y2, y3. We don't want to use previous values because those that have different information.
Oh, I see. Right. There's that. Right. Yeah. So here, give sampler, I guess, especially in the way that we used it in the past, is mostly, I guess, trying to draw parameter values, right? Where like we use theta 1, theta 2, all the kind of notations. So back then, we're trying to utilize what Sarah was saying, like what was done in the previous iteration. And specifically, we're talking about what we call back then full conditional posterior distribution, if you remember what that is. We are trying to write, let me see, if I'm talking about Gibbs. We're trying to get, like, say, theta 1 given theta 2 to theta p. Like, say there are p different parameters. And then we have this full conditional posterior distribution. That is theta 1 given everything else. And I should say also the data in here as well. Okay. Similarly, when I move to theta 2, I should also include my theta 1 that I just did. And then for theta p, and then all of the y. Now remember, we have those iteration index as well. I just say like s. So this is s from 1, s minus 1, right? And we were very careful back then, like to use those index correctly, because this should be s, but then this should still be s minus 1 and all that, right? Yeah. So back then we called them full conditional posterior distribution, and they're mostly working on parameters, whereas here we're doing it in terms of for the variable, like for the outcome itself. Even though, to be fair, give sample can be done on the data point as well. We did the beta binomial, I think. Remember, we're trying to replicate the paper, and then we're doing, anyway, one of the labs we're doing that, and that was not about parameters but about data points. So but yeah, so back then we have to condition on everything else, whereas here, yeah, I mentioned this mostly because I want you to make sure that all of the newly generated thing will go into the conditional, and just because, well, mathematically this is how it can work out. Okay, so well, I think in practice, when you are trying to do this for a project, for example, you would know what to do. Like you do Y1 first. Once you're done with that, make sure that you save them and then use that to model the next one and then generate the new ones. Okay, so, but this will be a good example, I think, here for us to keep in mind how things are being done. Question?
No.
Oh, okay. All right. Well, yeah. All right. So, couple of other things. So joint modeling and the full conditional specification. So I was saying that joint modeling, if you can do it, great. I mean, if you can specify a joint model, like I said, in 347, we haven't talked too much about it. And this intensive, we probably wouldn't talk too much either, just because FCS or like the sequential synthesis can be used pretty flexibly. But I do want to just give you an idea of what we mean by joint modeling. I mean, in practice, I mean, something can be done. So first of all, joint modeling is the ideal choice if the empirical data actually does follow up like a multivariate distribution that you can specify. So you'll probably be wondering what kind of we never learn any multivariate distribution. What can be one? So for example, if we go back to the CE sample, starting just the simplest case, I'm dealing with the log income and log expenditure. We have done it last time that you can use a simple linear regression as a model. And what I should mention is that back then we're doing partial synthesis, right? Partial synthesis meaning that we're fixing the log expenditure. We're also synthesizing, we're only synthesizing log income, right? But now if I ask you, okay, if I want to do a full synthesis for log income and log expenditure, what would you do? If you want to do it sequentially, what would you do? I can pause here. So trying to put what we just talked about, the sequential process, into practice. If we go back to the CE sample, we still have these two numerical variables. Now I want to do full synthesis for them, meaning that I want to predict both of them. Let's just say we're doing it sequentially. What would you do? All right, so if I'm trying to do a full synthesis for the two variables, log income and log expenditure, what would you do through a sequential synthesis? Ed?
We can synthesize the expenditure through rule and what's the other one? Race, and then use all three.
Oh, I see. Okay. Yeah. Okay. So I guess I was not clear. I was just saying that if you only have, but we can go that route, of course. But what if you only have the two? Like there's no race or rural, urban status. If I'm trying to do it sequentially, I have to do one first and then do the other, right?
Just go back.
Can you do back and forth?
No, because you just
If we have Y1,
doing.
say log income, log expenditure, just try to tie back to what we had earlier. Essentially, if there's no other predictors like the race or urban rural status, what we want to do is we probably want to do a marginal of Y1, right? And then do a conditional of Y2 given Y1. In a sense that, well, if I decide to do my log expenditure first, I don't know what I'm going to do. Maybe just like simple normal model with no predictors at all. Just guess, not guess. Using Bayesian methods to figure out the mean and variance and all that. And then synthesize Y1 from that model. And then I can do my Y2 given Y1, which is what we did before, when you have a simple linear regression, right? So this is what I mean. But what Tyler was saying is totally fine too. If you have the other predictors that are not to be synthesized, like X1, X2, let's just say X1 is race, X2 is urban rural area, urban rural status. Then you can probably factor that into your F1 fy1. So for example, this will become fy1 given x1, x2, right? And then this will be fy2 given y1, x1, x2. Okay. There's some subtlety. I mean, we have to take care of like how to build those models, but like conceptually, this is what you can do if you want to do a full synthesis from a sequential method. So that's all good. And what I want to introduce you now is a bivariate normal model. We never talked about it in 347, but essentially you can think about, like say, jointly y1 and y2. So y1, let's say, is log expenditure. Y2 is log income. Then this can follow a bivariate normal. So you can write bivariate normal. So all of the algebra, I wouldn't bother you doing that, but just so you know, for a bivariate normal, you're gonna have a vector mean, mu1, mu2, and then you're gonna have what we call a variance covariance matrix, in a sense that, what was it? So I think, what would be the good notation here? Sigma, yeah, so let me do sigma 1, 2, sigma 1, sorry, sigma 1, 1, sorry. I should just do, yeah, so the covariance matrix will be variance of y1 on the diagonal of y2. And then here is covariance of y1, y2. And here is covariance of y1, y2. Sorry about my bad handwriting. Let me actually just redo this part. Let me just use a whiteboard. All right. So here, I'm saying that I'm trying to model my y1, y2 jointly. Okay. You can have two continuous variables. Actually, you can build a bivariate normal model pretty easily. What we mean by that is you have a bivariate normal. You can write a big N with 2, just to show that it's dimension of 2. Okay. So what that is the mean is a vector of mu1, mu2. Okay. And the variance is now a variance covariance matrix. And then we use the notation variance y1, diagonal y1 and y2. And then the off diagonal is the covariance. Okay. So each of the entry here, each of this 4 entry is a scalar. Okay. But it together is a covariance matrix. So in short, we're just saying that y1 and y2, sorry, log income and then log expenditure, they jointly follow a bivariate normal distribution. Okay, so each has its own mean, mu1, mu2, that's fine. Each also has its own variance, which is all fine. So marginally, they each is a normal distribution. Okay, so from here, you can actually know that y1 is normal mu1 and variance y1. Okay, and then y2 is normal mu2 variance. Sorry, like variance. I'm just using this as a standard deviation here. So marginally, so when you have two variables jointly followed by bivariate normal, marginally each of them is a univariate normal. Okay, but what we also captured is this off diagonal term here. The two terms, they're identical. They're the covariance between y and y2. Okay, and we put it there just because and the math will work out in terms of the dimension. But pretty much covariance, if you remember it from your probability course, covariance is, well, definition-wise is a little tricky, but I just want to show you, well, not tricky, I just don't remember exactly what it is, but what I want to show is, you probably have heard about rho, which is the correlation coefficient. So correlation coefficient is obtained by the covariance between x and y, y1 and y2 divided by the variance of y1, multiply with variance of y2, and then take the, okay, so the covariance term is trying to capture in some way the relation between the two. Okay, but but it's a term that would go into the bivariate normal distribution. But at the end of the day, what I want to tell you is that you can easily specify bivariate normal, and in R you can generate. I mean, you can do random draws of those if you want, and then you can also, I mean, naturally all of those are parameters, right? So in Bayesian world, you give priors to them, you estimate what they are, and then you can then generate prediction out of it, and those predictions will become your synthetic data if you want. Okay, so if you want to use a joint model for two continuous variables, a bivariate normal one is a good one to use if you want. So the plot that I included for you here is not any model estimation. These are simply, just on the left is just a scatter plot of the original data. Okay, and on the right, what I did, even though I called it a simulation, what I really did is I was just actually getting, so you know that bivariate normal distribution needs two inputs, right? The mu vector, right? And then the variance covariance matrix, okay? So I'm not gonna write anymore here, but essentially I was getting from the original data, I computed the x bar one and x1 bar and x2 bar, and also their like empirical variance and covariance, and then I just put it in there, and I generate the same number of dots as in the original data, and just to show you what a empirical bivariate normal distribution will look like. Okay, so if you compare those two, well, the plots, I mean the dots on the right, they're more like concentrated, right? Whereas you have some like all of those over here, not surprisingly, because well, the original data would not exactly follow a bivariate normal distribution. And this is also what we were saying earlier, that when you're trying to use joint modeling, if the empirical data indeed follows a multivariate distribution, then you're good. Like I can just estimate the model and then I'm done. But a lot of times it's not. And this is just a quick illustration of, yes, if I use the empirical mean and variance covariance matrix, if I generate data from that, not doing synthetic data, this is just like get a sense of what a bivariate normal distribution is going to look like. Well, it's not the same as what the empirical data is telling us, right? So, but of course, you can still use bivariate normal model as a synthesizer if you want, and you won't get this. This is just like a direct simulation, but you can estimate, like I said, give priors to them, estimate it, and then generate synthetic data from there. But that's just an illustration of what we mean by joint modeling. And for, I guess, very small number of cases, it actually can be done. Just because, well, if you go back to the C data, you have so many different types of variables, what you're going to do, how can you specify a joint model for two continuous variables, one categorical and one binary, would just be too challenging, and then people wouldn't do that. And typically they would do this FCS, given what we have talked about. All right, so the last one, I guess I'll just mention before we break, is again, FCS not only like flexible, like easy to specify because you work with one variable at a time, and it can also be flexible to account for like certain kind of restrictions that you have for that particular variable, so that can just factor into the model itself. Okay, whereas jointly, you'll be really challenging. But of course, you never know if the FCS approach can guarantee a good approximation to the joint. And actually, we never know what the joint is in the first place. So there are always like work being done, like how can we best model this particular type of data? If I have a mixed type of data, what kind of approaches that we can do? So that is always being done. So what I would encourage you to think for our purpose is, well, there are many fancy methodologies out there. Our goal is to use those, I guess, advanced methods, if we can, as a Bayesian synthesizer, so we're able to maximize the utility of the data. Okay, but then soonish we will see that, well, when you maximize the utility, you might not get really a good risk profile. So then we have to do other kinds of stuff. Okay, so for Bayesian synthesis, again, we always want to make sure that the utility and risk trade-off can be taken care of, and then that will, yeah. So for if you're gonna, yeah. So once you start working on a project, you will make sure that you have to take care of both. But then along the way, we're gonna learn how to evaluate the utility. We already saw some today during the discussion, but we're gonna do that more formally for the next couple of meetings. And then later, we're gonna discuss how you can evaluate risks and then how you can do that, all right? And all right, so this was the example that I talked about. If you only have log income, so you can use a sequential modeling like that. All right, so I think I'm gonna break here just because, well, if I start on this, we're never gonna go back. But this one, yeah, so